the expectation of the proportion and the variance of proportion just follow directly from the properties of the binomial distribution. So you can see that the expected proportion is pi, the probability that the event happens, and the variance of the proportion is 1 over the number of trials times the probability times 1 minus the probability. And since the probability of the event happening is the expectation, then that gives us our variance function in terms of mu. So our 1 over ni is a constant, so that the part that specifies the dependence on mu is mu multiplied by 1 minus mu. Okay, and then the logic link, which we use in logistic regression, does the job of mapping the expectation, which can take values between 0 and 1, to the unrestricted range between minus infinity and plus infinity. So we can use other link functions to do this, such as the probit link, but the logic link is a particular example, and that's what was used in logistic regression. Another common example is log linear models, and in this case we're interested in modeling counts, which might follow a Poisson distribution. And assuming they do, then the expectation of those counts will be equal to the mean, and the variance will be equal to the mean. So in this case, our variance function is very simple. It's just equal to the identity function. The variance is equal to the mean. And in this case, we want to map from positive values, or 0, to, again, the unrestricted scale. And this is what the log link will do for us. So we model the log of mu. So these are two very common cases that you might not have perhaps sort of been introduced to in this sort of generalized way, but they all fall and can be sort of specified with the structure of a generalized linear model, and that's why we end up using the GLM function in R to fit them. And generalized nonlinear models are basically the same as GLMs, except now our predictor is nonlinear in the parameters. So we can't reduce it to that simple linear form where we have coefficients multiplied by random variables. So I've introduced it in terms of an extension of GLMs, but we can also think of it as being an extension of nonlinear least squares model, where we have a nonlinear predictor, but instead of assuming a constant variance that's where the error is normally distributed, we again allow the variance to potentially depend on the mean, giving a more general class of models. And the advantage of moving to a nonlinear predictor is it obviously gives us more flexibility in how we can describe the model. And in particular, in practice, this can mean that we can fit a more parsimonious model with fewer parameters and parameters that are more interpretable. So let's look at a basic example. This isn't one of our big case studies. This is a study of just over 1,600 children from Manhattan. It's an example in Agresti's book on categorical data analysis, where we have data on the mental health status and the parents' socio-economic status. And I've just plotted this using the mosaic function from the VZD package, which enables you to get a quick overview of a contingency table. So the size of the boxes is relative to the size of the count in the contingency table. And so we can get a first impression that as you move from the top socioeconomic class A to the bottom socioeconomic class F, then the numbers in the well category that have good mental health status decrease, and conversely, in the impaired category, you get bigger numbers. Whereas in the middle categories of mild and moderate mental health, there's not so much difference over the social classes. So it's mainly having an effect, it seems, at the sort of extreme ends. So if we're faced with a two-way contingency table, a very sort of basic analysis that we might do is to test for independence between the mental health status and the socioeconomic status using a chi-squared test. And this is equivalent to doing a goodness of fit test of the independence model, where we have the log expected count is equal to a row effect plus a column effect. So the mental health status and the socioeconomic status are completely independent. We just have additive main effects. And if we do such a goodness fit test, then that's essentially comparing this independence model to the saturated model, where we have a full interaction between the two factors, and it's saturated because we end up fitting a separate value for each cell in the contingency table. So these are two quite extreme models where we're saying the factors are either completely independent or we need to model each cell individually. So we might decide that there's not independence, but going to the saturated model seems a bit extreme and possibly over complex. And people have proposed intermediate models, and one such model is the row-column association model proposed by Goodman some time ago. And this is an example of a multiplicative interaction model, which is quite a common type of model in the generalized nonlinear model class. So here, instead of an ordinary full interaction, we have a multiplicative interaction, which is a product of a row multiplier and a column multiplier. So we end up with fewer parameters because you just have one for each row and one for each column, rather than one for each cell. So if we apply that to the mental health data, we've got three models then. The independence model at one end, if we add the multiplicative interaction, we find that it reduces the deviance by about 44 from a starting point of just under 48, with a reduction in degrees of freedom of 7. So that's a highly significant reduction in deviance. We've almost explained everything, all the variation in the data. And so if we move then from the multiplicative interaction to the full interaction, that there's hardly anything left for it to explain. And of course, it reduces the deviance to 0 because it's a saturated model, but the difference is not significant. So we see in this case that we can, and to move to the saturated model would take another 8 degrees of freedom. So in this case, we can describe the data very adequately with a much simpler, more parsimonious model. So that's introducing it sort of theoretically. And we have the GNM-R package, which is available to fit this type of models. And it's designed to be like GLM. So it has similar arguments, and you can use the same sort of methods on the returned object. And it will give equivalent results if you're just fitting a linear predictor. And if you use the Gaussian family, then it will be equivalent to an NLS fit. So linear models can be, linear terms in the model can be specified in the usual way. And but nonlinear terms, we need to specify using functions of class non-lin. And these are special functions that will describe the structure of the term, possibly also labels and starting values. And there are a small number provided in the package, but between them they can actually describe quite a few common models. So hopefully already quite useful. So there's exp if we want to specify the exponential of something, inv if we want to specify the inverse of something, mult is for multiplicative terms. Mult homog is a special case of that. So if we want to fit, if we've got a square contingency table where the two factors have the same levels, for example, an origin socioeconomic class and a destination socioeconomic class, then it might be reasonable to assume that the row effect and the column effect are equal. So that's what the mult homog nonlinear function does to fit homogeneous multiplicative interactions. And DREF is another special function which we're going to look at in our first case study, fitting diagonal reference terms. And you can also specify your own nonlinear function. It is a little bit tricky, but it can be done. And that tends to be more in scientific applications where you're modeling something like growth or a chemical relationship where there's some sort of theoretical nonlinear function underlying the relationship that you want to describe. So that doesn't tend to come up so much when we're thinking about official statistic applications. So if we go back to our row-column association model that we saw for the contingency table, this is how we'd fit it with the GNM package. So we're using the function GNM. Our frequency is the count in the table. Then we've got our two main effects for socioeconomic status and multiple health. And then the multiplicative term is just the mult of those two factors. It's a count, so we're using the Poisson family. We've got our data there, mental health, and then just a couple of extra arguments for both, so we're not getting so much outputs. And of interest picks out the coefficients of interest. So when we print the model or we print the coefficients, it will only show those coefficients from the multiplicative term because we can end up with quite a lot of coefficients in these models. So sometimes it's helpful to sort of say, well, I'm only really interested in these ones and just return that. So now we'll think a bit about the parameterization in the models. So when I presented the independence model, it was in an over-parameterized form. So we had the log of the count, the expected count, is a row effect plus a column effect. And we can add a constant to the row effect and compensate for that by subtracting the same constant from the column effect and end up with exactly the same model. And this is a general problem in models. And what's normally done in a linear model or a generalized linear model is that some identifiability constraints will be automatically applied. And there's usual constraints in R, for example, in LM or GLM, are to set the value for the first level of the factor to 0. So the first row effect and the first column effect will be 0. And then the other effects are differences to that reference level. In GNMs, it's a bit more complicated. So for example, if we look again at this row-column association model with the multiplicative interaction, if we add a value, say 1, to the row multipliers in the multiplicative term, we can compensate for that in the row main effect by subtracting phi c there. Alternatively, we can multiply the row multipliers, for example, by 2, and compensate for that by dividing the column multipliers by 2 and getting exactly the same model. So in this case, we need to constrain both the location and the scale to get identifiability. And in general, for generalized nonlinear models, it's not so straightforward as it is in linear models to define some general rules for how to constrain a model. Sometimes you need to constrain location, sometimes location and scale, sometimes location, scale, and rotation in multi-dimensional space. So it can get quite complicated. And GNM just avoids this problem, essentially, by working with over-parameterized models. And what this means in practice is it will return one of the infinite parameterizations at random. So it's not a made-up result. You know, the fitted predictor is well-defined. It's just that the parameterization is arbitrary. What this means is by default, we'll find that the nonlinear parameters and sometimes the linear parameters, if they're dependent, will not be identifiable. And you'll see this in the result by the standard errors being NA. And this is fine for general model building, comparing models, and so on. And then once we've got a model of interest, we can constrain the parameters that we're interested in as required. Sometimes it's not necessary to actually constrain them and get identifiability parameters, because we might only be interested in a subset of the parameters, for example. But we'll see how this works a bit in the case studies. So here's our first one on diagonal reference model. And the background is that we're using data from the Office of National Statistics longitudinal survey, which links census data and vital event data for 1% of the population of England and Wales. And our objective is to study the effect of social mobility on long-term limiting illness, which is defined as a long-standing illness, health problem, or handicap that limits a person's activities or the work they can do. So the data we have include the National Statistics Socioeconomic Classification, which has 7 classes from high, manual, or professional to routine. And we have that at the origin year, which is 1991, and a destination year of 2001. In other words, at one census and the next. And we also have data on the age and gender. So these data were studied by Bartley and Lewis in 2007, and they modelled the trajectories of people from origin and destination by comparing by combining social mobility effects with origin or destination effects. So, for example, in the origin and mobility model, they included a term where we have the origin effects, alpha I, and then an additional term, delta 0, 1, or 2, depending on which describe their mobility. So there's delta 0 as if they were moving to a more favourable class from 1991 to 2001. Delta 1 is if they were in the same class in the 2 censuses, and delta 2 is if they moved to a less favourable socioeconomic class. And the destination and mobility model was basically the same, but instead of an origin effect, alpha I, it had a destination effect. So the full model is a logistic regression because we're modelling the probability of long-term limiting illness in this case. And these are linear models because we've just got constant effects in the model. And so we can fit these with GLM. So here we've got GLM of our the probability of long-term limiting illness with a predictor with age in 1991, the origin effect and the mobility effect that I just described. Yeah, it's a probability, so we're using the binomial family, and in this case we modelled men and women separately, so that's why I've got the underscore M there for men. So if we fit these 2 models, the origin and mobility model and the destination and mobility model, we can take the exponential of those mobility parameters, those delta parameters, to get the odds ratios of long-term limiting illness, for example, for men, where we take the moving to more favourable as the reference, so that's odds ratio of 1, and compare that to the stable or moving to less favourable. So we can see that given origin, the odds of long-term limiting illness are increased by downward mobility, moving to less favourable groups. And given destination, the odds of long-term limiting illness are decreased by downward mobility. So these are sort of 2 sides of the same story. We can evaluate these models by looking at the weighted residuals. So we can take the working residuals from the GLM fit and average them over each origin-destination combination to give an indicator of fit for each trajectory. And we can standardise these residuals so that they're approximately a standard normal, assuming the model is correct. And we can plot them again using the mosaic function, and that also returns a p-value for the goodness of fit test. So here's the residuals for these two models. And although they are essentially two sides of the same coin or two sides of the same story, they capture slightly different features of the data. So we're getting some large residuals in different places. So in the origin and mobility model, we've got a large negative residual for individuals that started in class 2 and moved to class 1. And on the other side, we've got a large positive residual for the origin class 3 moving to destination class 4. So those are the sort of largest residuals, but the general pattern of residuals is not sort of symmetric. They're describing slightly different features of the data. Another way we can approach this data is to use the diagonal reference model, which was proposed by Sobel in the early 1990s. And this combines the origin, destination, and social mobility effects all together. So what it does is it takes a weighting of what are called the diagonal effects, or an effect, which are the effects for the stable individuals, so the ones that are in the same class in both the origin year and the destination year. And for those that aren't in the same class, it takes a weighting of those effects for the origin diagonal effect and the destination diagonal effect. So this is a structured main effect because we're sort of taking a weighting of the origin and destination effects rather than just adding main effects of origin and destination in the model. So we can fit this in GNM using the DREF term that I mentioned earlier, and it's actually quite general, so we can have more than two factors, but in this case we've just got the two factors, origin and destination. And the weights need to be non-negative and to sum to 1 for the weighting to make sense. And so this is implemented by parameterizing them as the exponential of a delta parameter and dividing by the sum of these exponentials. So that will make sure that the weight is positive or non-negative and sums to 1. So it's the deltas that we actually estimate in the GNM model. So following the previous analysis, we can fit this model with age as the covariate and fit models for men and women separately. That's what we're doing in the code here. So instead of the origin plus mobility, we've now got DREF of origin and destination. And if we look at the coefficients for this model, we see what I was talking about earlier, that most of them return a standard error of NA. Only the age, which is a linear term, has a standard error at this point. So let's think first about the diagonal effects. So if a person is in the same origin and destination class, then the model for those individuals is just an ordinary logistic regression, where we have an intercept plus beta 1 times the age, and the diagonal effect for the class that they're in. And if we set the diagonal effect for the first class to 0, then these diagonal effects are the log odds ratios of long-term limiting illness in a particular class against the first class for a given age. And I just show that here. So this is a log odds ratio of some of LLTI in some class I compared to the first class, and the beta 0 and the beta 1 times age cancel out, and so we're just left with the gamma I, because the gamma 1 is 0. So that gives us, enables us to constrain these parameters. So you can see here now I've got the first diagonal effect set to 0. So that doesn't have a standard error because it's fixed, but all the others are then estimable, and we can attain standard errors. And there's now no dependence with the intercept, so that also now has a standard error. So that just leaves the the weights, which are parameterized by our delta parameters. Oh, I was going to say a bit more about the diagonal effects first of all. Yeah, so now we've identified them, we've got standard errors. We can plot these, and these give us an indication of the health inequality between classes. So these are for individuals who are in the same class in both censuses, and we can look at the odds ratios of the long-term limiting illness in the different classes compared to the high professional class. And so we can see the general trend of increasing odds ratio as we go to the more manual and more routine classes. But we do see some differences between men and women. The odds ratio is higher for men, in particular in classes such as the intermediate class, the semi-routine and the routine class, perhaps indicating that they're more likely to take on manual work in these classes, which has an effect on their health. Now, come back to the diagonal weights. In this case, as I say, we're estimating the deltas, and we can set the first delta to 0, and that will be enough to constrain the weights. And we can go back and refit the model doing that, and we'll get a standard error. But it's actually the weights that we're interested in, and so we have a convenience function to compute the weights and their standard errors using the delta method. So that's what we do, what I've got in the code there. So how do we interpret the weights? So the ratio of origin weight to destination weight quantifies the diluting effect of social mobility on health inequality. So health inequality is captured by our diagonal effects, and it's these weights that will quantify the effect of social mobility. So, for example, if we put all our weight on the origin effect, then social mobility has no effect on the individual because they're just taking the effect of their origin class into their new class. It doesn't matter where they go, it's all about the origin. On the other hand, if all of the weight is on the destination effect, then social mobility has no effect on inequality because a person moving to a new class just takes on the characteristics of that class, and it's not changing anything. So if the classes are unequal in their health, then social mobility isn't changing that. And in all the in-between cases, then social mobility increases the probability of long-term limiting illness in the upper classes and decreases it in the lower classes. And the larger the origin weight, the greater the diluting effect. So in these data, we see that the origin effect is bigger for men and the destination effect is bigger for women. So since the destination class is given more weight, this means that social mobility has a greater impact for women. So we can compare the diagonal reference models to the origin and destination plus mobility models that Bartley and Lewis estimated. And we can see that what's in the table here is the difference in deviance from the null model. So we can see, for example, that the origin plus mobility model reduces the deviance by 4,050 with a difference of 9 degrees of freedom, and so on. And what we see here is that the diagonal reference model reduces the deviance the most, even though it requires fewer degrees of freedom in the model. So again, it's more parsimonious model, and it's a single model rather than sort of trying to fit two models that capture slightly different parts of the story. Right, our last case study is the Lee-Carter model. And this is for modelling mortality data. And our data come from the Human Mortality Database, which provides open international access to population and mortality data from 41 countries. And we're going to consider deaths for men, aged 20 to 99 in Canada from 1921 to 2003. And what the data we have are the year the death was recorded, the age at time of death, the number of deaths, and the exposure, the number of people at risk in that year. So Lee Carter proposed a model in 1992 for age-specific population mortality rates, and this has been used quite a lot in subsequent analyses. So the model is this. We suppose that the death count, DAY, for individuals of age A in year Y has a mean, mu AY, and quasi-Poisson variance, phi times mu AY. And this is because we expect over-dispersion in mortality data. So we need to allow for this by estimating a dispersion parameter rather than fixing it to 1, as in the Poisson model. Then the Lee Carter model says that the log of the expected rates, which is the expected count over the exposure, is equal to an age effect plus the product of an age multiplier and a year multiplier. And just using the properties of logs, we can take the log exposure onto the right-hand side into the predictor with a fixed coefficient of 1. So if we want to fit this model in GNM, we can do it as follows. So we've got GNM of deaths and modelled by MALT of exp, age, and year. So we're using exp here to constrain the parameters that represent the sensitivity of age group A to have the same sign. So these are the age multipliers. It only sort of makes sense if they're either all positive or all negative, and by using the exponential, we can constrain them to be positive. We could fit the age main effect in the model in the usual way, but here we're using the eliminate argument of GNM. And this is useful when you have a model that instead of an intercept has a factor with many levels as the initial term in the model. And this can, by using the eliminate argument here, GNM will exploit the structure of the model and estimate it more efficiently. So you end up with an equivalent model, but it will be quicker and more efficient if we use the eliminate argument here. The log exposure term is specified by an offset because that's got a fixed coefficient of 1. And as I mentioned, we're using quasi-Poisson here rather than the Poisson family. Okay, so if we fit the Lee Carter model to our Canada data and look at the residuals, what we find is that the over-dispersion isn't equally distributed in the data. And we see that residuals are more dispersed for particular age groups, for example, 25 to 35, and particular periods, such as pre-1930. And if we look at the cohort, which wasn't in the model, in other words, the calendar year minus age, we see a clear trend in the residual. So there's obviously some sort of cohort effect in these data. Renshaw and Haberman proposed a cohort-based extension to the Lee Carter model. So what we've got here is the log of the expected rate, and then the first part is the Lee Carter model again, with the age effect and the product of the age multiplier and the year multiplier. Now we've got an extra term, which is an age multiplier and a cohort multiplier. So this is quite easy to specify in GNM. We just add another multiplicative term, but it's not so easy to fit because, as we mentioned, cohort is directly related to year and age. And in general, it's harder to fit models with multiple multiplicative terms, especially when we have many parameters. So now we've got 405 multiplicative parameters. And in fact, Renshaw and Haberman rejected this model as being impractical. But it is possible to fit with GNM. you need a little bit of care. So we can do it by, first of all, fitting a GLM where we fix all the age multipliers to 1, and then fit the full model that we're interested in using the starting values from this first step. And here we do that without constraining the age multipliers first of all. So if you remember before, we were using X for age to constrain them to be non-negative. And this model converges in a reasonable number of iterations, 54 iterations. What we find is that the multiplier for age 99 is negative when we don't put any constraints. So in other words, it's on the boundary of the parameter space. So all the other ones are positive. This one is negative. We want them all to be the same sign. So we refit the model, now constraining the age multipliers to be positive, and fix the parameter for age 99 so that it's effectively 0. And now if we plot our residuals, or plot the equivalent residuals for this model, we have a much better picture. They're centered around 0, much more even dispersion across, or certainly age is very neat. The year is a bit more bumpy, but you don't have these specific periods where there's a lot of over dispersion. And similarly for cohorts, again, perhaps a bit bumpy, but a lot better than we had before. So an advantage of reparameterizing those age multipliers as the exponential of another parameter delta is that then the simple contrasts, in other words, the differences between the deltas are identifiable. So in other words, we can set one to 0 and look at differences with that reference category, as we have done with other parameters. And GNN provides a function getContrasts to help estimate such contrasts. It can do a little bit more than simple contrast, but that's all we need here. So first of all, we need to pick out the coefficients that we're interested in, which we can do with the pick_coef function from the package. So this is just picking out the age multipliers in the multiplicative interaction with cohort, and then passing the model and the names of those parameters to get contrasts. And I've got check equals false here, so I'm not going to check if these parameters are identifiable. I'm just going to assume, because I know what I'm doing, and that saves a bit of time. And this returns a QV object, which is from the QV calc package. And part of that object is a QV frame, which gives us the estimates, the standard errors, and the quasi-standard errors and quasi-variances. And these quasi-standard errors have some advantages in some cases. In particular, you'll notice that for the age that we fixed to 0, or that we may fix the multiplier to 0, the standard error is then 0, but for the quasi-standard error, we still have a non-zero value, so that they're less. The quasi-standards are the same regardless of the reference level you take, whereas for estimates and standard errors, the standard error will change depending on the reference. So they are sometimes useful. In this particular case, though, the approximation doesn't work very well, so we're going to stick with the estimates and standard errors just to plot some estimates and approximate confidence intervals. And this isn't some ggplot2 mistake here. Those error bars or confidence intervals at the end, really do become very, very large. So we find for ages above 85, 86, there's a lot of uncertainty in what the log multiplier is. But for earlier ages where we have more data, then we get quite tight estimates, quite tight confidence intervals. And we can see a general pattern here where the log multiplier is gradually increasing as we get to about age 35, and then it starts to decrease. So rather than fitting a separate estimate for each age, we could consider some types of spline. And here we're just going to consider a piecewise linear spline, which we can define using the BS function from the splines package. And we're just going to assume a linear spline where there's a linear piece for every 5 years. And the first line there is just converting the age factor into a numeric variable in order to define the spline. And then once we've got that age spline, we can use that in our model instead of the age factor. So let's take a look at what we've got. So these models aren't nested. We're not doing an analysis of deviance here, but the Lee Carter model had a deviance of over 30,000 on 6,399 degrees of freedom. So a lot of over dispersion relative to degrees of freedom. And simply adding a simple one. Yeah, just having the main effects of age, year, and cohort already gives a much better model. We've got about the deviance is about 2/3 of what it is in the Lee Carter model. And then our Renshaw-Haberman model, which is the extension with the age cohort multiplier, sort of is another big shift down to about 10,000 deviance. So if we take the main effects model as 0 and the Renshaw-Haberman model as 100% in terms of the deviance, then the model with the spline explains nearly 84% of the deviance. So the spline is giving us a very good approximation of the Renshaw-Haberman model, which was quite difficult to fit. And another advantage of the spline model is that we're only changing our model for the age part, and it preserves the year and cohort multipliers. And one thing that Renshaw and Haberman proposed is modeling these multipliers using time series methods for forecasting. And this only depends on the differences between multipliers. So we don't need to constrain these parameters and make them identifiable in order to do this modeling. So I'm not going to do that here. Obviously, we don't have time, but it sort of shows that the potential. All right, so that was what I wanted to present today. If you want to find out more about GNM and look at more examples, we're starting to collect some case studies with reproducibility materials on this GitHub here. So far, we've got the Lee Carter model that I presented. We can't share the data, but you can access the data yourself if you register with the Human Mortality Database. And there's another example of using the UNIDIF model, which is another contingency table type model. We hope to add examples of this diagonal reference model. Again, it's going to be a bit, we'll have to simulate some data a bit or something because we can't share the data directly, and an example of rash models. And these are cases that we're using in a working paper with David Verth and Yanis Kosminis, another collaborator. And the GNM vignette has even more examples. Some of them are simpler examples, not necessarily sort of deep examples like these case studies of different models that you can fit with the GNM package. And some of them are also covered in a half-day course and a day course that I've given on GNM, which again you can find on my GitHub if you want a bit more support going through the examples and some exercises if you want to work through those. And that's it. Those are the references I had. if you want to find out more about those particular examples or models. Thank you very much.
Thank you, Heather, for a really interesting talk. I would now like to open the floor. We have room for 1 or 2 questions. I don't see a question. I don't seem to see a question in the chat. I will ask Anna if there was a question on the YouTube channel, or if somebody wants to ask a question who's in the WebEx, then please make yourself known. Otherwise, I do have some takeaways myself. I think actually I have to apologize. I think I said generalized linear models, and when I announced it, but it was generalized nonlinear models. I swallowed the non. The Lee-Carter model that you talked about reminds me very strongly on a model that we use to estimate numbers of species. So we make statistics about nature, and volunteers are counting butterflies and frogs and all kinds of animals, and we have to impute for that. And the model is, I think it's exactly or almost exactly as the Lee-Carter model that you explained here. So the GNM package would be really worth for us to look at. I did have a question, because I'm definitely not an expert on generalized nonlinear models. I often even mispronounce it. And that's about interpretability. You did a very good job on explaining how to interpret certain coefficients and results, like in terms of the diluting effect of social mobility. So I also teach linear models to students, and then the coefficients, they have a unit. So you can say the use of fuel goes up by this much if the volume of the engine goes up with 1. And this already gets a bit more difficult with generalized linear models like logistic models. And how do you see that in generalized nonlinear models? Because the coefficients are sort of hidden even further inside the model. And do you think, and it's maybe also a general question, can software help us to make this interpretation easier?
Yeah, you're right. It can be more challenging to interpret the parameters in a nonlinear model, and I guess we try and well, in some cases we can get back to the type of interpretations that we can do in the generalized linear models, for example, by looking at the log odds ratios of certain things, and then often we're thinking in terms of sort of multiplicative effects instead of additive effects. So it's not as simple as sort of saying a difference of so many units gives this a direct effect. So it can be a bit more challenging, and you have to think a bit harder about the particular models. I don't think that's so different from other types of nonlinear model. In terms of whether software can help us, not too much directly, I don't think, in terms of the interpretation. So we have that get contrast function, which, as I mentioned, is a little bit more general than I showed, for sort of pulling out and making identifiable contrast. So it can also cope with situations where you're trying to constrain the scale, for example, as well as the location. So we can give a bit of help from software, but I think it does come back to sort of thinking about the model and about the mathematics and how that works in the particular case.
Yeah, so we still need to talk to our statisticians.
I'm afraid so.
Cannot make ourselves completely oblivious. Okay, thank you once again very much, Heather. Before we move on to the next session, I would just like to note that Heather will come back to us or stay with us because Friday we have a panel discussion on research software engineering, and I'm very happy to announce that Heather will join us there as well. So thank you again, and I pass the floor to Alex, who will chair the next session.
Thank you, Mark, and welcome from my side. We have the next session, which is called data cleaning, with 4 presentations and 1 lightning talk. And you know the mode. If you are in the WebEx meeting, you can just enter questions already during the talk for the presenters. And if you're on the YouTube channel, just write down the comments. We have a colleague who will forward the questions into this meeting. So without taking any more time, I would like to go for the first presentation, which is given by Kazumi WADA from Japan, long-standing participant of uRos, so in person in many occasions. Please, Kazumi, you can start sharing your presentation. And as soon as we see that that's working, you can start presenting.
Okay, Alex, thank you.
Yeah,
hello.
Looks good.
Can you hear me?
Yes, we hear you fine.
Thank you. Hello, my name is Wada Kazumi, working for Statistical Research and Training Institute in Japan. Today, I'd like to talk about a multivariate outlier detection method named MSD. MSD is an abbreviation of the Modified Style Donoho estimators. In 2018, I made a presentation in uRos about comparing 4 different multivariate outlier detection methods for practical application to a national survey, and MSD was selected. Actually, the work was for data cleaning of hot tech donors. So this year, I decided to prepare a GitHub package of MSD. A related paper regarding the comparison of methods is available here. Definition of outlier depends on the purpose of activities, but in this presentation, we define an outlier as observations in the tails of the distribution. This scatter plot shows the difference between robust and non-robust methods, together with the difference between univariate and multivariate methods. In a data cleaning step for numerical variable, we often decide an appropriate value range and examine extreme values out of the bounds. Some people use mean and standard deviation to decide the range, but this is a bad idea, as you know, since outliers in the dataset affects the value of mean and standard deviation. The rectangle shown in pink color is a data range made with mean and standard deviation. A better method is using more robust tools such as interquartile range or a box plot. The green rectangle in this scatter plot shows a data range made by a box plot. As for multivariate method, we can draw probability ellipses using the mean vector and the covariance matrix. It is shown in orange lines here. It's not robust as same as the range made by univariate mean and standard deviation. The red probability ellipses are drawn by MSD. The method conducts robust estimation of a mean vector and the covariance matrix. Univariate methods create rectangle data range, while multivariate methods create ellipsoids. These plots also show the effect of outliers. If data follow a multivariate normal distribution, there's not much difference between robust method and non-robust method. However, numerical survey variables often have longer tails, even after data transformation. As I explained, the univariate method have rectangle bounds. When there is no correlation between numerical variables, we do not need multivariate method. But problem arises when there are correlations between variables like this. See the observations shown in red color in the scatter plot. They look like outliers, but are unable to detect with univariate methods. In this case, any multivariate method is necessary. But so far, I'm afraid multivariate methods are not widely used, perhaps because of the following reasons. The first reason is the best method depends on the situation. So there is no one best method for every situation. And therefore, the detected outlier depends on the method used. So one problem is no unique solution for multivariate outliers. And the next reason is it is more difficult to figure out the reason of outlierness sometimes. After detecting outlier using an automatic tool like this, someone will have to check the outliers and find how to treat them. But finding the reason of outlierness could be more difficult than univariate outliers. About 20 years ago, there was a project named EuroEdit. This project covers the field of data editing and imputation, and advanced multivariate outlier detection methods are also examined. You can still get the documents on the website. One of the project reports introduced that MSD is practically used for survey data editing in Statistics Canada in 1990s. And the project also suggests a few improvements on the algorithm. Since there was no software at that time available, we implemented both the Canada version and the improved EuroEdit version, and then confirmed the suggestions of the EuroEdit improves the performance. This is the outline of the method. It's a bit complicated. The first step is generating many orthogonal vectors. One of the suggestions of the EuroEdit is increase the number of vectors here. Then next step is projection. Probably it's better to use this slide. Select one vector and calculate and make a projection on this vector. Then calculate the median on this vector and decide weights for each observation. If one particular observation is quite near from the median on this vector, the weight would be quite near from 1. But if it is very far from the median, the weight is reduced, and finally it will be 0. This procedure is repeated for every vectors. And after finishing the projection, now one observation will have weights as many as the number of vectors created in the first step. Then we select the smallest one among them for the observation, for each observation. The next step is weighted principal component analysis. We can get a set of principal components. It is also a pair of vectors. And again, we made a project. We select first component, and made a projection, calculate median and weights, and after finishing all the principal components, we find the smallest one weight for each observation and calculate weighted mean vector and covariance matrix. This is the output of the function. And based on the robust estimation of the mean vector and the covariance matrix, Mahalanobis distance is calculated for each observation. Outliers are decided using F statistics. The recommended threshold is 99.9 percentile point of F statistics. So the basic idea of this method is look at the data set from many different directions and find observations in the tail of the distribution. So I cannot scroll the page. Now you may understand that increasing the number of projections improves performance. But it also causes the problem of the curse of dimensionality. The number of projections increases exponentially along with the increase of variables. The implemented function can process up to 11 variables with 100 observations on a 32-bit old PC with a maximum 4 GB memory. It's not so big data set, so we also made a parallel function using do parallel and for each packages. So parallel function together with an IEEE conference paper is available regarding this work. For this year, this is my previous work, and for this year, I revised function MST and its parallel one for this conference, and make an RMST package, but run out of time due to some problem with such as dependency of use packages for parallel version. So I just put RMST inside the package on GitHub. And regarding the parallel version, its function name is rmsd.p. It's inside this repository. It's not in the shape of a package, but at least you can get the function itself, so that you can use it if necessary. And lastly, I would like to briefly introduce the usage of function RMSD. I mean the single core package in single core function in the package. It's quite easy to use. I just incorporate the final outlier detection step inside the function and remove unnecessary unnecessary intermediate values. Installing this is for installation, and load the package and load the data here. This example is using the dataset named stars SHUIZ inside the robust space package. It's one of the very famous test dataset for robust estimation. Usage is quite simple, just to put the data set inside the function. And this is the result of, you can plot the result. This return value contains a flags of outliers. If observation is not outliers, the value of this one is 1. But if an observation is regarded as outliers, the value will become 2. So please see the scatter plot as the detected outliers are shown in red color. this function also provides final weights. It will help to determine the adjustment of the threshold to decide outliers. If the observation is quite near from the center of the data cloud, the value of weight is nearly 1. The weight near to 0 means it's quite extreme outliers. There is another example with 5 variable dataset also inside the robust space package named, the dataset is named aircraft. This time I try the different threshold. The default setting is 9.
Kazumi, not visible and we cannot hear you anymore. Are you there?
29 depends on because vectors deciding the direction to see the data set differ
No, you're back.
based on the random numbers.
Excuse me, can you just
So-
like start again from like 20 seconds back because you were disconnected for a short period of time.
Oh, really?
Yeah, but just 20 seconds, I guess. So we still got that you introduced the dataset from the robust space package, but then shortly after it stopped.
Okay, so probably number 28 or 7.
No, on this slide, on the slide you were on.
Okay,
just
okay.
when you started talking about the aircraft dataset that is also from robust space, then it stopped from me.
Okay, thank you. This method is using random numbers. So the outcome could be slightly different, depends on the execution, because of the random numbers. So we can put random seed here. So if you use the same, we use the same random seed, the result is exactly the same for the same data. In this case, we just we also change the threshold to decide outliers. So the first, this is a real result of the first execution. One outlier is detected, but with different threshold, 2 outliers are detected. But the result of Bernhard distance are exactly the same with these 2 executions because of the same random seed here. Because of the but the threshold is different. This is a plot of the test statistics here, and the threshold for the default setting is shown in blue color, and the threshold with 95 percentile point is shown in cyan color here. So because of the difference of the threshold, the number of outliers detected are different. Now, I guess I'm running out of my time. So questions and comments are welcomed. Thank you very much for hearing.
Thank you very much. I have a question or a comment by Mark. Thank you for the interesting work. Very nice method. I would like to ask if you have tested the method on economic SBS, for example, variables like turnover or profit. These are very skewly distributed and have a long tail as well as a high linear correlation. So the question is, have you tested that on real or not real skewly distributed data, such as variables from economic surveys, such as the structural business survey? And I would like piggyback one question on that. Is that research work, or have you applied that in a official statistics setting? So is that done for in the production of statistics?
Okay, thank you very much for the good question. First, I just tested using a random data set, some normal distribution and QT distribution and so on. But they differ from a real data set. The real data sets. So we also tested with some economical data sets. The paper shown in the slide 2. As a recent paper published as the Australian Journal of Statistics, this method is tested with real data sets. As I told in the beginning of the talk, the best methods differ from the station of the data sets. So probably it is necessary to test with a real data set before practical use, I think.
Okay, thank you. Another question is how would you handle categorical data in your methods? Is that something you can deal with?
Well, so far this method is only for the numerical data sets. So so far I do not work on the categorical data sets. But usually the survey data sets contain both categorical data and numerical data. So I usually use categorical data to stratify, to divide the data set in similar, with similar settings, and then conduct this kind of method for the numerical variables.
Mm. Thank you. And the last question is a complicated one. Does Gram-Schmidt projection normalizes any type of multivariate high-dimensional mixture, or some assumptions are necessary in order to apply these algorithms? It's maybe you can ask that in writing in the chat, because we're already quite ahead of time. You see the question in the chat window, and you could type your response there. With that, thank you very much for your presentation. We have to move on to the next one. Thank you, Kazumi.
Thank you very much.
You're still sharing the screen, so please
really?
press the stop
Just
button.
a moment, I will cancel it.
Thank you. Oh, it's coming up again.
Oh.
Yeah. So the next presenter is Andrei TEMPL from the Hungarian Central Statistical Office and Corvinus University of Budapest.
Yes, hello, I'm here.
Hey, that's good. So maybe you can start sharing your screen, then you override Kazumi. Yeah, that's good. We see the PDF.
Okay, so can you see it?
Yeah.
Okay, so thank you very much,
Start.
and thank you for having me. So my name is Andrei TEMPL. I'm a PhD student at Corvinus University of Budapest, a statistician at the Hungarian Central Statistical Office. And today I want to talk about identifying outliers with density-based methods, especially in housing statistics. So the outline for this presentation is going to be the following. I'm just going to talk briefly about the problem of outliers, and I'm going to rewrite on the previous presentation. Then I'm going to introduce this density-based outlier detection methods with a heavy emphasis on the local outlier factor, so the LOF method. And then I'm going to compare these methods on rental data available for us, which is an online rental data for housing statistics. And then I will try to summarize what to do with outliers. So the basic problem of outliers is, why do we want to get rid of those? Is pretty easy, because they have a significant effect on our data analysis. So if we are trying to fit a linear model, then it will distort it pretty heavily. But however, there are cases when it can be also the center of attention. So for example, in sports statistics, we want to highlight those observations which are different from the others. So like sportsmen who outperform the other people. And the definition of outliers is not exactly clear, especially in multi-dimensional settings. So I got this graph from Agarwal and Yu. So this is like the same database, but from different views. So we can see that in view 1, a data point is clearly an outlier. But in all the other views, it is actually an inlier. But in the 4th view, B is an outlier, where everyone else is an inlier. So this is one of the problems with outliers. Multiple dimensions make them harder to identify. So the goal of this presentation is not going to talk about the best technique, because I firmly believe that there is no best technique for outlier detection, but looking at different methods. So the data I'm going to use today is an online advertisement data for housing rents. It's from ingatlan.com. It's a Hungarian advertisement website, which is pretty much the largest advertisement website for housing rents as well as housing advertisements. So we have a pretty big database. I'm only going to restrict this database to one region, which is the Pest region, and only for 1 year. Because I do not want to deal with time and spatial discrepancies. And I'm only going to consider 2 dimensions in this case. I'm going to consider price, because that is our primary interest in housing statistics, and the area, which is pretty good for housing statistics, because the area is a very strong predeterminant of the price of the dwelling. This is only due to interpretational purposes. So the methods I'm about to show you, they work really well in multidimensional settings. However, it is well, it's really hard to like do ggplots in 3 dimensions and to interpret these. So this is why I would just do with 2 dimensions. So these density-based methods, what they have in common really is that they are dealing with local density. And what it really means is that they take the nth neighborhood of an observation, and they're trying to calculate its density. So how many observations are in there, or how dense the observations are in that dimension or in that neighborhood. And they're comparing it to the neighboring observations' local densities. So the idea behind this is that the scarcer the area around one observation is, the more likely it is to be an outlier. So this is pretty much the key idea. And examples include the dbScan algorithm, which I'm not going to talk about today, but the local outlier factor, which I'm going to get into it a bit more deeply, and the feature bagging outlier detection, which is in essence an iterative version of the local outlier factor. I chose the local outlier factor because it's pretty much the starting point and the gold standard for these local densities. Okay, so how is this done? It has been developed by Breuning et al. Around 2000. And what we want to do is that we want to first get the local reachability distance, so pretty much the distance for each point to the kth neighboring observation. So for example, this is from the original paper. Here we are considering the third neighbors. So this P point is clearly an outlier, where these are inliers. So we take the third neighborhood, so first one, second one, and the third one. We draw a circle, and we're pretty much calculating a density in this. So this is in 2 dimensions, but this works. It's designed to work in n dimensions. Then it will calculate pretty much a density in an n-dimensional Euclidean space. So here we have the P points density, and then we have the local densities of these neighboring observations. And as we can see, these densities are much higher, so that the circles, in essence, are way smaller than the outlying ones. So the probability of this being an outlier is pretty high. So so this we are calculating the LOV score. I also included the calculations here, which is essentially we are comparing our local density to the neighboring local densities. And the resulting LOV score is something that if it's an inlier, so it's not an outlier, it should be around 1. And if it's the further it is from 1, the more likely it is to be an outlier. So this is pretty good because this is a clustering method. So if we have multiple observation groups, we can identify those and not falsely identify individual observations. So if we had a lot of observations here, a lot of observations here, then this could be then identified as an outlier. And so it's more effective in these kind of cases. So the problem with this is well, it has a couple of problems, but for most of them there are remedies. So the first problem is that the choice of K is non-trivial. So the choice of how many of the neighborhood of the neighboring observations should we take into account. The original paper says that it should be at least 10, and it also the idea behind this is that the smaller the K is, the more emphasized the locality becoming in this local outlier detection. But so obviously we can use the old trial and error, but if you want to do some more methodologically better ways, there is, for example, Sony, what they did, they estimated first the KNN algorithm, and with that they could estimate the optimal K for this local outlier factor. And Zhang et al., what they did, they first estimated the dB scan, and based on the dB scan, they could estimate the optimal K value, and then it could be applied. So this problem can be solved. The second problem is that there's no clear threshold for the LOF score. So again, the closer it is to 1, the more likely it is to be an inlier. But there is no clear threshold, say from 1.6 onwards, it's an outlier. For this, there are a couple of things we can consider. First, we can just omit the top 5% of the LOV scores as observations and mark them as outliers. Or there is another algorithm by the same authors called the local outlier probability, which assigns probabilities. And as statisticians, we like to deal with probabilities rather than these rather objective or subjective methods. There is also a problem with duplicated data. So in the previous one, there are divisions. So this basically arises when by duplicated data, I mean where there are data in the same coordinates. So if there are 2 data which are the same and we choose K to be 2, then essentially the local outlier factor by definition is going to be infinite. So it cannot be really dealt with. So there is this problem with duplicated data. I will show you that this is actually not that big of an issue. We can either omit the duplicated values, or we can just add a small noise to these data, to these coordinates, so it will not distort the whole analysis, but we'll deal with this duplication error. And there is one that is potentially lengthy calculation. So our very big databases, we need a lot of memory, and also it's for each data point we have to calculate a lot of these densities. So it's not that straightforward. For this, there is an algorithm called FastLOF, which can be applied. The syntax, in fact, is very simple. We can use the RLOF package, and it's really we just have to put in the data and the K parameter, which we already had. There is the feature bagging outlier detection. I'm not going to dwell on this that longer. It's, in a sense, an iterative version of the local outlier factor. So we choose just the proportion of the observations available, and then we're going to calculate the local outlier factor calculation like 100 times or so, and then we will get these scores. This can be calculated using the HiDMAUS package. I highly recommend checking out this package because it includes also various other outlier detection methods. So for example, there are the angle-based method and there is the robust version of the KNN method. It's really useful and I highly recommend it. So, and again, we just need to get the data inside it, validate the iteration number and also this KNN, which is the K parameter in essence. So here are the results that I have for this database. I didn't mention the backplot. The backplot in essence is a two-dimensional box plot. So it is really good to identify these core observations that we're having, but the problem is that it will mark many of the observations and outliers. So first of all, this FBOD is very similar to this this backplot. So obviously there are more observations here marked as inliers, but it marks these observations as outliers. So in essence, it will really get this feeling of core observations. And regarding this duplicated and non-duplicated data, here we can see that there are small differences here. So for example, this is problematic, but this is due to overfitting and can be dealt with a better choice of K. But in essence, the marked outliers are pretty much the same in these cases. So so both versions, both using it with duplicated data and without duplicated data is viable. And another thing that I want to consider is that the local outlier factor can be used as like preliminary data cleaning like thing, because so what here I did this whole local outlier factor with just omitting 5% of the data, and then I also built a model on this whole multivariate database. And then I calculated the Cook's distance, because the Cook's distance prerequisite is to fit a linear model or some sort of model. And then it will calculate the outliers based on that. So what we can see is that we had to do a pretty good model, and the results are going to be pretty much the same. So yeah, there are differences due to the multi-dimensional thing of the database, but as a preliminary just data cleaning service, the local outlier factor is very good. And also I included the Cook's distance with 1% of the data. I did not include the local outlier factor for 1% of the data, but they are very similar in this case. So as a summary, because I know I'm running out of time, why should we care about outliers? It is very good to dive into the outliers because they are very good for understanding our data. So for example, when we dived into the outliers in this data, we found out that some of the more expensive and some of the more expensive houses were actually not houses, but castles for rent. So that is very useful to look at. And I really want to emphasize that there is no single best way to evaluate outliers, at least I think, and as I read a lot about these things. So, and it's really worth to explore many of the possibilities that we have. And I want to close up with this. I saw a couple of methods and applications regarding this, where what they did, they calculated outliers with 3, 4, or 5 different methods. And if, for example, if 3 of those methods marked an observation as an outlier, then they indeed treated it as an outlier and omitted it from the database and went on with the analysis without that. So with that, thank you for your attention. I have these references here. And thank you for having me, and I wait your questions if you have any.
Thank you. Very interesting presentation, and thank you also for the kind of connection to what you actually would do with the outliers. In that direction would also be my question. I'm just quickly checking the chat and giving everybody the opportunity to put something there. In the meantime, one question. from me. So we saw your pictures, and the nice example of the castle was actually quite good. That, I mean, an outlier somehow in the statistical setup, an outlier is more thought of like an error, but in the world of real data, outlier could be an error. Then it's good that it's detected, but could be also a castle. So it's a correct value, but strange. I'm not sure how you use that in the statistical office, but there are different applications, obviously. Like if you want to compute the total, you cannot cut off the outliers. If you want to compute important factors, so like a regression, you might exclude them. Do you have more insights on when you would actually, or what you would do with the outliers?
Yeah, this is a very interesting question, because I really dwelt into this outlier problem, because we try to analyze these outliers, and I quickly realized that it's not really a statistical problem, but it's a philosophical one. So, and I do think that because of this, this is why we should use multiple outlier detection methods, because while they not be still the best, but they can still help us to decide on what to do outlier, and what to mark as an outlier and what not. So if we have multiple inputs, then we can, how should I put it? We can rationalize omitting these variables from the data set. But yeah, this is a very hard question, and I think it should be addressed more.
Thank you. One question in the chat from Jan is, you might have missed it, but do you scale and transform, for example, take the log for skewed variables before you apply the LOF method, or does the LOF function do that itself?
Okay, so I did not scale the input variables. It can work also with scaling the input values. I did not scale those because I really just wanted to do like a preliminary data cleaning. So I did not want to, let's say, put a final, so finalize the observations. I just wanted to, because we got this new database, we didn't really had idea on the whole Hungarian rental market. So just basic data cleaning and getting to know our data better. So we have these, well, not quite clean data, but a way cleaner data to analyze it further. So this could also be used as like a first step for data cleaning. So that was my point.
Okay, thank you. Thank you for answering the questions. We have to move on already to the next presenter.
Okay, thank you.
Thank you again for the presentation. Jeva Purakausket, I might have pronounced it quite wrongly, from the Statistics Lithuania will present next.
Yes,
So please,
hello, I'll share my screen. Okay.
Yes, it works perfectly.
Yeah, as it was already mentioned, I'm Jeva Burakauskaitė, a chief specialist at Statistics Lithuania, and today I'm going to share the results of an outlier detection study that was carried out while working on my master's graduation thesis. And the thesis supervisor was Dr. Vilma Nekrašaitė-Liegė, a lecturer at Vilnius Gediminas Technical University, who is also an employee at Statistics Lithuania. So I'm going to shortly introduce selective editing, the method for outlier detection, then a contamination model for calculating predictions, and the results of all the study. So first of all, what is selective editing? Well, it aims to identify errors that have a major impact on the quality of sample estimates. And by identifying the most influential observations, the data editing procedure could then be focused on these observations, saving statisticians from the unnecessary data editing. And that's why the outlier detection study was carried out. The main focus of it was to optimize the data validation procedure in Statistics Lithuania using selective editing. So let's start with the assumption that only a part of statistical survey data contain error. So therefore, data can be separated into two different parts, one being free of error and the other one contaminated. So the Formula 1 denotes unobserved data model. Those data are not erroneous, and Formula 2 denotes observed data model, where diagonal elements of the matrix I indicates whether the corresponding observation is erroneous or not, and when an influence of this erroneous observation is then conveyed through an additional random noise, which is denoted as epsilon in this formula. So, as I mentioned earlier, selective editing aims to identify the most influential errors. Therefore, it is important to rate all the observations, all the errors, depending on the influence they have on the quality of sample estimates. And this could be done by constructing a score function. Formula 3 here denotes a local score function. Its estimates indicate an influence of some observation of one of the indicators. But when more than one indicator should be considered, it is worth using a global score function instead and calculating one unambiguous score instead of a set of different local scores. And while I'm still here, going further into the presentation, it will be important to take into consideration a suspicion component, and this suspicion component is denoted as S in Formula 3. Here it is. Now about the suspicion component. Well, before defining it, let's separate data errors into two different categories. First one being non-statistical errors, for example, observations that do not fall into some previously defined interval. And statistical errors, for example, observations that stand out compared to some additional information. And statistical errors could be identified by checking whether a corresponding value of a constructed test variable falls into some chosen acceptance region. And basic test variable could be a combination of variables from a statistical survey or some additional information. Now about a discrete suspicion component. Its structure is pretty simple. It equals to 1 if an observation is non-statistical or statistical error, and it equals to 0 otherwise. Whereas a continuous suspicion component has a little bit more complex structure compared to a discrete suspicion component. Well, it again equals to 1 if an observation is a non-statistical error, but when an observation is a statistical error, it also depends on the distance between the observation and one of the boundaries of a chosen acceptance region. Therefore, 3 additional parameters are included into formula of this continuous suspicion component, and those parameters are kappa, alpha, and tau. Package CELMX of the statistical programming language R was designed to apply selective editing in practice, and 2 main functions of this package were used during the study that I am talking about. The first one, ml.est, is designed to calculate contamination model predictions. The second one, cell.edit, is designed to calculate score function estimates. And I want to point out that I added these two functions here with arguments that would be the default arguments, but in the second function, cell.edit, the argument weight is also multiplied by s, and this s here stands for our suspicion component. Now speaking about the study that was carried out, it was carried out using statistical data from the quarterly statistical survey on service enterprises of Statistics Lithuania. And the target variable of the study was enterprise turnover of the accounting period. 4 different predictor variables were used, and therefore 4 different statistical data sets were obtained that were full. I mean, they did not consist missing values. Today I'm going to talk about 2 predictor variables, that is turnover from value-added tax declarations and total hours worked. So firstly, when predictor variable was turnover from VAT declarations, the scatter plot here shows the dependency between the target variable and predictor variable. As you can see, this dependency is quite high. Correlation coefficient is close to 1. Out of approximately 4,000 observations, a little bit more than 2,800 outliers were found, but only 136 influential errors were identified. And later on, those identified influential errors were changed into the corresponding contamination model predictions. And this new clean data set, 5% of observations in this clean data set were contaminated in 3 different ways. That is 1.5% of observations multiplied by 100, 2% of observations trimmed, leaving only the first and the last digits, and 20 million was added to 1.5% of observations. This scatter plot shows the dependency between target and predictor variables after the contamination that I was talking about. Red dots represent contaminated values, while blue dots represent observed values that were not contaminated. Outlier detection was carried out using different level of accuracy. And then the level of accuracy was picked in such a way that, well, if all the detected influential errors were introduced by the data contamination procedure, then the corresponding level of accuracy was chosen for the further study. With predictor variable turnover from VAT declarations, this level of accuracy was chosen to be 0.011 for both selective editing with a discrete and with a continuous suspicion component. Later on, these influential errors were edited one by one, and relative absolute bias was calculated after every edit. This graph shows a relative absolute bias dependency on the number of edited influential errors. When selective editing with a discrete suspicion component was used, 134 influential errors were identified, but after calculating relative absolute bias, it turned out that only 92 of those influential errors have to be edited in order to reach the desired level of accuracy. But using a continuous suspicion component, the number of influential errors identified was lower, and that meant that almost all of the identified influential errors had to be edited. That is 92 out of 93. And this example shows that continuous suspicion component could help us to reduce this unnecessary data editing. The second example is when using total hours worked as a predictor variable. Out of approximately 5,000 observations, 158 influential errors were identified. All of those influential errors were then changed into the corresponding contamination model predictions. And this new data set was again contaminated in 3 different ways that I have already mentioned before. Again, selective editing was applied with different levels of accuracy, and this time level of accuracy for the further study was chosen to be 0.026. That is bigger than with the previous example, and this shows that while using turnover from VAT declarations as our predictor variable, we could achieve a higher quality sample estimates. Relative absolute bias was again calculated after every edit. When using a discrete suspicion component, it turned out that the desired level of accuracy is still not reached after editing all of the identified influential errors. But using a continuous suspicion component, almost every influential errors have to be edited in order to achieve the desired level of accuracy. And this example again shows an advantage of a continuous suspicion component. So 2 final remarks were made. Selective editing with a continuous suspicion component was determined to be a better outlier detection procedure, since it lets us to avoid unnecessary data editing, and turnover indicators were identified as the most suitable predictor variables for the outlier detection procedure. And the main property of a suitable predictor variable turned out to be a high correlation between the predictor variable and the target variable of the study. In the last slide, I added a few main references. So thank you for your attention. And now I could answer your questions if you have some.
Thank you very much for that presentation. I give everybody a few more seconds to enter the questions into the chat. Before that, a short advertisement announcement, because your presentation and also the other 2 presentations before you would also perfectly fit in a statistical data editing meeting. And soon there will be a call for the 2022 statistical data editing meeting by the UNICE. That just came to my mind. One question I have is how the reception from like subject matter experts or data clerks were on your presented methods, because that's something we frequently discuss at these meetings, that it's difficult to explain to such methods to experts who previously manually looked for data outliers or suspicious data points and then kind of edited that manually. Do you have any experience with that? How you communicate such methods to them?
Do you mean to experts in statistical Lithuania, for example? That
Exactly, yeah.
Well, actually, not long ago we had this lectures on these new methods for outlier detection and for data editing in general for our experts that have been working in Statistics Lithuania for a long time. So I still am I'm waiting for the response to those lectures.
So, but it is used already in production, right? Did I get that?
Yes, it has been used, the selective editing, but the main, well, one of reasons why I did this type of study was to improve the existing method. So the suspicion component led us to find a way to improve the methods that were used, the selective editing that was used. So yes, it was improved.
Great. We don't have a message, a question in the chat. So thank you again, and thank you for answering my questions. And we will move on to the next presentation, which is given by colleagues from Statistics Portugal. Bruno Lima will give the presentation. Please go ahead and start sharing your screen.
Good morning. I think you can see.
Good morning. That seems to work. We hear you a bit. It sounds a bit low, but
Can you hear me?
it should be all right. Probably you have to speak loudly so we can hear you all right.
Okay, I will try to.
Yeah, okay, that
speak
works.
loud.
Thank
Okay,
you.
thank you.
Go ahead.
My name is Bruno. Good morning. I'm from Statistics Portugal. Here I will present you a work in progress where we use R for data quality. More precisely, we'll talk about the e-invoice case, as we call it. Okay, some background. Focus on the use of administrative data has been a constant throughout the years at Statistics Portugal, aiming a significant impact on the reduction of statistical burden, as well as the possibility of returning new statistical indicators to society, more urgent and adequate to the decision-making needs. About the invoice, Statistics Portugal receives monthly from the Portuguese tax authority more than 80 million records regarding taxable amounts aggregated by issuer and acquires fiscal numbers. The amount results from invoices issued by individuals or legal entities that have their head office or permanent establishment in the Portuguese territory. Records are obtained from an implemented mandatory e-invoice system as part of the administrative simplification and anti-fraud measures from the Portuguese authorities. So about data quality, we can say that to become statistical data, administrative data must be treated and validated to ensure its quality, reliability, consistency, and completeness. In this data cleansing process, an in-depth and specific analysis of anomalous data is performed. So, our aim is to implement a procedure to detect anomalies on observations received from the invoice and impute new values to these anomalies. This is the structure of our data. We don't have too many variables. We have the year of the records, month of the records, issuer's fiscal number, issuer's NAS, acquires fiscal number, acquires classification, number of records, and finally, monthly total value for the pair issuer acquired. The main packages used in this procedure are those from Tidyverse, also Oracle, an Oracle database interface driver for R that allows us to process our data. Targets, a pipeline toolkit to maintain a reproducible workflow. ISO3 for implementation of isolation forest algorithm for outlier detection and imputation of missing values. And InputTS for imputation of missing values in univariate time series. So basically, we work with time series at two levels. First time series at level NAS. We have monthly taxable values for each NAS. NAS meaning statistical classification of economic activities in the European community. The other level, time series with monthly taxable values for the pairs issue acquire within each NAS. So we want to implement an iterative procedure for anomalies detection and the detection of values to replace those anomalies. So basically, we start identifying anomalies at level NAS. We look for time series at level pair issue acquire with a contribution of at least 10% of those anomalies. Then we identify anomalies at level pair issue acquire. And when anomalies agree at time point between level pair and level NAS, we input values, and finally we reveal this time series at level NAS. Okay, a little bit more in detail. We start building time series for each issuer classification, the level NAS. So we do that grouping our data by NAS and summing monthly total value. We have a total of 145 time series, and to those we apply the isolation force algorithm from the package ISO3 in order to compute the probability of an observation being an anomaly. We also try to apply the isolation force algorithm to all the data as a multivariate analysis, but we couldn't find the anomalies we are looking for, probably because the values are too different between the NAS. So to define the cutoff value for the probability of anomaly, let's call it a score, we built a Helmholtz curve with the number of anomalies detected from different scores within each NAS. And here you can see that for a score of 0.55, 6,150 anomalies are detected. For a score of 0.7, 254 anomalies are detected. For a score of 0.8, only 9 anomalies are detected. In this curve, this curve is probably around 0.55 and 0.7. Here in these examples, we will consider a score of 0.79 for the identification of anomalies, because in the first step we want to treat only the more severe anomalies. Those are more obvious errors. So we use the score of 0.79 at level NAS, and then when we go down to the level pair, we will use a score of 0.7. With a score of 0.79, we detected anomalies in 19 NAS. Those are the values and the respective probability of anomaly. Now I will show you 6 examples of those previous anomalies for 6 NAS, and here you can see time series of each NAS, and in red are the anomalies identified by the isolation force algorithm with a score of 0.79. So for each one of the identified anomalies, we'll look for those time series at level pair issue acquire with a value at least 10% of the anomaly within the respective NAS. With the selected time series at level pair issue acquire, we apply the isolation force algorithm now with a score of 0.7 for anomaly identification. For consistency, anomaly identification level pair is made only with variables year month and total value as performed at level NAS. The imputation of new values is made when the anomalies at both levels agree in time point, year month. This imputation is made using the Kalman's moving algorithm on structural time series models from the InputAS package. We also do an imputation using the isolation force algorithm, and I will present you the results. Okay, for the first NAS, this is the time series at level pair issue acquire that we found with the contribution of at least 10% of the anomaly. We applied the algorithm for anomaly identification, and no anomaly is identified, so no imputation is done. for the second one. This is the time series found at level pair. When we apply the algorithm for anomaly identification, two anomalies are identified, although the imputation is done only for the first one, because it's the point that agree in time with the anomaly at level mass. For this other NAS, in this case, we found two time series with a contribution with 10% of the anomaly. We applied the algorithm for both. For the first one, no anomaly is detected, so no imputation is done. For the second one, an anomaly is detected. The imputation is done with method Kalman smoothing and the isolation forest. Here you can see that the value inputted by Kalman smoothing is higher from the value inputted from isolation forest. Another example, here also we found the two time series. For the first one, although you can see here, probably this is an anomaly, but the method do not identify it, probably because you don't have enough points. So no imputation is done. For the second one, the method identifies two anomalies, but again, we only include values for the first one, and in this case, the value from isolation forest is higher than the value given by Kalman smoothing. Another example is the identified founded time series at level pair. Here they identify anomaly and the inputted value. And the last example, for this NAS, we found three time series at level pair with a contribution with 10%. When we identify the anomaly in the three time series, we found it, and the imputation here by Kalman smoothing and from isolation forest. In this case, in value given by isolation forest are even higher than the initial anomaly. So that's why don't work for us in these cases the isolation forest for imputation, and we go for the Kalman smoothing. So in last part, we want to understand, we want to see how the imputations we made at level pair impact time series at level NAS. So we rebuilt those time series at level NAS with the new value. On the top, you can see the original time series and with the previously detected anomalies. On the bottom, the new design of the time series with the imputations. For the first case, no imputation is made, so the time series are the same. Here in the second case, you can see the value input. Other two examples, in this case, we have imputation for both the anomalies. Although the new values are lower than the previous one, probably in this case, we still have an anomaly. So that's why we need to, again, implement the iterative step, another step to identify, to try to see if we still have an anomaly. And the last two examples, we have the original anomalies identified and the new values imputed. In this case, both the values are in the range of the other points of the time series. And as a conclusion, you can say we built a rather naughty pipeline to identify incorrect anomalies from invoice data. However, we believe that with this procedure, we can improve data quality without incurring any other corrections issue. And that's all. Thank you.
Thank you, Bruno. Just for your information, the microphone is still low. I'm not sure, do you give the next presentation as well?
Yes.
Okay. So maybe while we wait for a question, you could also, or in between the two presentations, you can raise the volume of your microphone, so it's easier for everybody to understand.
Okay, I don't know how can I do this because let me see.
If you go to the speaker and microphone settings, you could increase the volume. There's a slider.
Okay, I will try to stop sharing.
But before that, I have one question myself. You're doing a lot of, you do like a searching for anomalies, outliers, and also imputation, or with that changing values in your data set. How do you kind of monitor or log the changes to the data throughout this process? Do you have like a log file where you see in which step you edit data points? And do you make like a statistics that in this process step you changed things and so on? Can you say something about that?
The procedure is built with the targets packages, so all the steps are recorded, and those new imputations, we have a data table with the new values and the old ones, and we can compare them. So the new values are very different depending the NAS they belong to, because those classifications, we group the values have too many different values. And in this phase, what we want to do is to identify those anomalies, those more severe anomalies that are clearly errors, not going to trying to find every outliers or possible outliers in this time series.
Okay, thank you. I don't see any question in the chat, so I think we could move on to your next presentation.
Okay, just tell me if you can hear me better now. I'm trying to put the volume up.
I turned the volume on my computer up so I can hear you all right, but I guess it's also the difference between the two of us. So probably I'm loud and you.
Okay, I'll try to speak louder because the microphone volume is at the maximum also.
Okay, so no, I think it's all right. It should be able. Everybody should be able to handle it by turning its own volume up. So please go ahead and start the next presentation.
Okay. So this is a shorter presentation. You probably want to go to lunch, so let's do it more quickly. In this case, I will show you how we use R for quality control on the simplified business information. Again, some background about simplified business information. It is a mandatory annual declaration for enterprises and individuals with organized accounting. It is delivered electronically and collects in a centralized way information for accounting, tax, and statistical purposes. Implemented since 2007, Simplified Business Information has been a facilitator to enterprises' compliance with their legal obligations. One of the quality controls for simplified business information uses data collected through Interstat by International Trade Department from Statistics Portugal regarding annual amounts of enterprises' imports and exports. Interstat is a system used to collect data on trade of goods between the EU member states. It is a specific survey done by intentional sampling to all enterprises subject to VAT and with a transactions amount above an annual threshold value. Data from simplified business information is joined to data from Interstat for a group of select enterprises and their values are compared. The main package used in this procedure for quality control are those from Tidyverse. Also validate, require validation rules and data quality indicators, PC modify to modify data using external rules. These last two packages from Mark van der Loo and Edwin. So in our procedure, as inputs, we have database tables for quality control and a table with predefined rules. These last table have a set of rules and transformations we end to do to our data sets according to those rules. Those validation rules are created based on business knowledge, and the procedure we use the package validate to create and validate an object with the function validator. Then we confront the data with our rules using the confront function, and then we can plot the results for each data set, those observations that pass or fail in which one of the rules. Here are the results for 3 rules applied to one data set. For data cleaning, we want to create new variables based on the predefined rules. So the rules are transformed in if clauses, and a dot file is created as an argument for the function modify. Finally, the function modify is applied to our data, and all this process is implemented on our Markdown report with the option meet with parameters. When we run this option, we just have to give our dataset, the dataset we want to clean, and a final result is presented in a HTML report with a downloadable data. And that's all. Thank you.
Thank you very much. Good to know that people are using the tools that are presented in previous editions of this this workshop, this conference, because we also already had a validated tutorial, I think 2 editions ago or something like that. So that's very nice to see applications of that. So is there any question, or is everybody already moving on to lunch? Let me see. I don't see anything in the chat. No. Yeah, so I think we will also join everybody to go for lunch. It's a break now from now until 1:30. So in about an hour, we will start again with a session on methods for official statistics. Yeah, enjoy your lunch. See you then. And one more information, so the next YouTube link will be available on the website in 5 minutes.